of Production Logistics Management and of the JKU Business School. He received his PhD in 2015 from the University of Vienna. He has received several awards already, among which is the Dissertation Award of the Austrian Society for Operations Research. Inform Section Location Analysis also awarded him with a PhD award for his dissertation. He was a postdoc at the University of Vienna. Then he spent some time at the INRIA in Lille in France. And now he is at the JKU. He has published more than 40 papers in prestigious journals such as Management Science, Operations Research, and he has recently completed his habilitation work. And last but not least, before I give the floor to Markus, I would like to mention he has also been ranked among the top 30 researchers under the age of 40 in the last BWL ranking, which is also quite an achievement. And now he has, besides the business school project, also an LIT project, and the business school project is going to be presented to you today. So please, Markus, the floor is yours.
So thank you, Sophie, for the nice introduction. And let's share the screen. So yes, so this is about my business school project. I'm very happy to be able to present it to you all. So the topic, the name of it's OPTIM-AI or optimal, depending on how you want to read it. It's hybridization of optimization and artificial intelligence techniques for managerial decision making. So where are we exactly? We are in the area of business analytics. And where are we there, in which subfield? So if you look here, this is the analytic value escalator from Gartner, a consultancy. And you see that there are, for example, descriptive analytics, diagnostic analytics, predictive analytics, which answers questions like what happened, why did it happen, or what will happen. And we are in the area of prescriptive analytics. We want to answer the question, how can we make it happen? And this is typically the area where in a company, the most value can be added using analytics, but it's usually also the most difficult area because here you then really need optimization and foresight because you really want to do decisions about the future. And how do we achieve to do this in a meaningful way? We use techniques from optimization, and here we focus on mixed integer programming. This is a very powerful modeling tool, mixed integer programming, and it can be used to model so-called combinatorial optimization problems. And many business decisions can be modeled in such a way, because in combinatorial optimization problems, you can model decisions like, should we open this facility or not, or should we buy this thing or not? You can encode this in a mathematical way and then put it into some constraints like, I only have this budget to buy all these things, and so on. And also you can deal with uncertainty and so on. So it's a very powerful modeling tool, mixed integer programming. But for solving these problems, in a theoretical sense, if you maybe have some computer science background, this is an NP hard problem, such mixed integer programming and also combinatorial optimization problems usually. And so it's not known if there is an efficient algorithm really to solve all these problems or not. So, and in particular, when the problems become large and larger, which happens now with big data, we want to solve large and larger problems. This becomes hard to solve. And so in practice, there exists software to solve software packages from companies like IBM. They have solvers for such mixed integer programming problems. But so they are able to find the proven optimal solution for real world problems, often in reasonable time. But again, when the problems become larger and more involved, you have more site constraints, then it becomes harder and harder for using just such off-the-shelf solvers you can buy. But just to show you that this is not just an academic problem, mixed integer programming, but it has real impact. Here just collected 2 abstracts of recent papers in the Inform's Journal of Applied Analytics, where they show that the big impact mixed integer programming modeling is making in the business world. For example, here is an example of Vattenfall, which is a wind farm wind farm company, one of the largest wind energy companies in the world. And they used mixed integer programming modeling for wind farm design, and they had experienced a net present value gain of more than 150 million euros by using the results of this modeling. And also Volkswagen is using this in their pre-production center for capacity scheduling for product. and there they have cost savings in the 6-digit euro range. So just to show you, mixed integer programming really has an impact for business. So, but then the question is, okay, so there are these off-the-shelf solvers which can solve maybe some of the problems. So where does the research come in here? So these solvers, they use theoretical insights, so mathematical insights, and also careful software engineering, because this is really hard to make successful solvers. So you need to combine these two areas. But there are many problems where still the solvers, they fail to give you an answer in reasonable time. So what you need to do here is where really the research comes in. The solvers need to be improved all the time, and or you even need to use alternative solution approaches for this kind of problems using advanced algorithmic and mathematic techniques to enhance the solvers. Okay, and in this project we try to do this from the perspective that we want to use tools from predictive analytics and artificial intelligence like neural networks and so on to improve the existing mixed integer programming solvers, or maybe even replace the solver, these existing solvers with tools like neural networks. And this is a very hot and emerging topics, which in the last years gained traction, that researchers started to look into similar topics, and we also do this. So in a nutshell, it's can we learn how to solve mixed integer programs, or can we learn how to solve mixed integer programs better? This is the question we are asking in this project. And there are many different streams where you can go there. And in this talk now, in the reminder, I will talk about one of the areas we focused. Here we took a problem which we know how to solve it as a mixed integer programming problem, and we wanted to see what can we do when we use neural networks. Can we also use them and get good results? So this means the first ingredient we need to talk about is a problem which can be formulated as a mixed integer program. And here we took the vertex-center problem. This is it's a classical problem from the area of location science. And of course, location science, as we had production logistics management, finding the right or optimal locations for where to build like facilities is always a very important topic in our area. So we focused on this. And this concrete problem, you are given a set of locations. For example, you can take the municipalities of Upper Austria as potential locations. Then you're given a number which tells you how many locations we can open. And then we have distances from each of the locations. So this is the input we have. And what do we want to decide? We want to decide where to open locations. For example, it could be whether we want to open fire stations or so on. So where we want to build them. And we want, our goal is that the maximum distance of any location to its closest open location is minimized. So again, in the context of fire stations, you can think, okay, the fire brigade needs to go everywhere very fast. So you should locate them in such a way that over all the locations, that the maximum distance to its closest fire station is minimized. And this is a potential application area. You could even maybe think about where to locate vaccination stations, because then also it's maybe good that the maximum distance to the next vaccination station is minimized, that people have an incentive, not that they don't have to go so far. And to see a concrete example, here we took as centers to compute the distance, we took the population weighted centroid for each of this municipality of Upper Austria. And if you then put P is 12, so we can open 12 locations. This is the optimal solution. This is we achieved with using mixed integer programming. We obtained this optimal solution. And so here you see where you would open the locations and which is the nearest. The coloring gives you essentially which the nearest locations. Yeah. So this would be a solution. And in mixed integer programming, you would formulate this now in the following way. So you don't really need to understand the model. It's just that you have seen it once. You would define variables where you say these 5 variables tell you, for example, is this location opened or not? And these other variables tell you if this location gets assigned to an open location, to this certain open location or not. So you have these 2 sets of variables, and then you build the model, and then you put constraints like the first one tells you you can only open P location. So the second one tells you that each location needs to be assigned to an open location. And for example, the third, number 4, tells you if a location gets assigned to an open location, then of course this location where it's assigned to must be opened. And this is how you build models in the language of mixed integer programming. And this you can then give for a concrete instance like Upper Austria to your solver, and the solver software after some time will give you a solution. So this is the normal, the traditional approach. And what we want to find out in the project is, can you use alternative approaches? And to do this, we used we want to look at graph convolutional neural networks. So what are they? So first, what are neural networks? So what do neural networks do? You are given some input, and then some black magic happens, and then the network tells you if the picture you just gave your network is a cat or a dog. Or in graphic way, you have a picture of, this is, I guess, a cat, and then you take some representation of this image. For example, you could take all the pixels of this image and you feed it in the so-called input layer of your network. Then there are also hidden layers, which you don't kind of know about so much. So the hidden layers are where the magic happens. And then you have the output layer. This is where you are interested again, because this output layer tells you then, is this a cat or a dog? And here we have a badly trained network, because for this picture, it tells you this is with 62% probability that this is a dog, which is probably not the correct answer. So in a more formal way, what happens in neural networks? So you're given some input, and then mathematics happens in the network, which then decides in which category the input belongs. So this is neural networks for classification, which also our approach will use in a certain way, the neural networks for classification. And so how does this look with a little bit less cats and more mathematics? We have some input here with the input layer. So this could be some number, like kind of the pixel, which color the pixel has. And then here we have this hidden layer where mathematical functions are occurring, which combine the inputs. And then we have the output layer, which again combines the output of the hidden layers to give some prediction, and the prediction is, for example, is just a number or so. And then if the number is maybe 1, it's a cat. If the number is 0, it's a dog. But the network will give you out maybe 0.7. And then you say, okay, this is maybe a cat because it's nearer to 1, which for us is a cat. And this is usually trained, so in a supervised manner, these networks. This means you already start with like many samples where you know this is a dog, this is a cat, and you feed this network with all the pictures. And then with mathematics, with stochastic gradient descent, it gives you weights for these functions. And then the idea is then later on, when you give new input to the network, which it has never seen in this training procedure, that these weights are still good weights also for the new pictures you give, that it can still correctly predict if it's a cat or a dog. And so this is how neural networks for classification more or less work in one slide. And now what's happening in neural network for combinatorial optimization problems on graphs? So this really emerged in the last 3-4 years as a topic. And this is still a very open topic where the results are promising, but they're still very far behind. Just to say this at this point, they're still very far behind traditional tools for prescriptive analytics, like mixed integer programming. This is really a topic, an area in its infancy where there's still much basic research to do. But the basic question is, given a problem on a graph, and then predict which nodes or edges should belong to the optimal solution. In our case, it's which locations should be opened in an optimal solution. And here we see a basic architecture from a state-of-the-art neural network approach for the so-called traveling salesperson problem, which is one of the most fundamental problems in whole of prescriptive analytics. So here you have as an input a 2-dimensional graph. Then you use so-called graph convolutional neural networks, which are again a very recent development. And then you get a prediction for the edges, like a heat map, which gives you for all the edges a certain probability that the solution. And then with these probabilities, then you feed a post hoc algorithm, which really transforms you this in a true solution, which in a TSP case is a doer. So this is state-of-the-art approaches, architectures. And what we did, we wanted to see, okay, these architectures have mainly been used for this traveling salesman person problem. What can we transfer this also to other problems? So we, in this recently submitted paper, which I did with my colleague Elisabeth Gar from also the Institute of Production Logistic Management, we wanted to see, okay, can this approach also work for other problems? So we basically followed this neural network architecture in this state-of-the-art work. This was implemented in Python using PyTorch and PyTorch geometric our neural network. And then as a training set, we fed it with 100,000 instances with 50 locations. Of course, for NP is 5. And of course, for this, as we use supervised learning, we solved this with mixed integer programming to get the optimal solution for our test set. And now we know which locations are opened. And this is our training set. So, and this we give to train our network. And then with a test set with 10,000 such instances. And then on the test set, we check how good is the prediction, which location should we open. Okay, so what were the results? So for the results, of course, we need algorithms to take the probabilities the network gives, because maybe for 10 locations, it gives some probabilities that this location should be open, but we have just P is 5, we can just open 5. So we need an algorithm to transform the probabilities into really 5 open locations. So we used a naive algorithm, which really takes the locations with the P locations, the 5 locations with the largest probability. And then we also used another algorithm, which we denote as greedy, which is a little bit more sophisticated, taking into account symmetries of the problem. So this a little bit better transformation. And then also for comparison, we used the baseline algorithm, which is the same as greedy. So greedy gets, of course, fed by the probabilities of our which our neural network predicts. By the baseline algorithm just is fed with random probabilities. And in the end, we see the greedy algorithm works better than the baseline. So this means our output of the neural network, we learned something. So this is, of course, the optimality gap to the true optimal solution, which we know, again, by mixed integer programming. So we see it works better than the baseline, but maybe there's still room for improvement. But again, this is not surprising, and this is consistent with state-of-the-art work for also other problems in where neural network are used for these graph optimization problems, because there is really still much to do to compete with established mixed integer programming approaches. Okay, so these are our research findings in this area. So, and this will conclude my talk. So thank you for listening. And if you have any questions, yeah, feel free to ask them.